All right, let's get right into it. Today, we're going deep. We're going past the engine, past the wiring, and straight into the electronic brain of the vehicle, the engine control unit, or ECU. We're going to get this thing on the bench and really demystify what's going on inside, piece by piece. Okay, let's kick things off with a situation we've all seen. You've got a car in the bay, it'll crank all day long, you can hear the fuel pump priming, but you've got absolutely no spark. You've checked the coils, the plugs, the wiring, and everything looks good. That's when that little voice in your head tells you the problem's got to be deeper, right here, inside the ECU itself.
So you know what that means? We're going to do what every good tech loves to do. We're going to take it apart. Let's pop the cover off this ECU and start our diagnostic journey. We're about to turn what looks like a crazy puzzle into something that makes perfect sense.
Yeah, I know. At first glance, it's a lot. It looks intimidating, right? A whole city of tiny chips, coils, and little components. But stick with me. By the end of this, you're going to be able to look at a board just like this and see a logical system, where every single part has a specific job to do.
So to make sense of all this, the first thing we need to do is divide and conquer. Every single one of these components on the board, it falls into one of two families. They're either active or they're passive. Understanding this one simple difference is really the key to getting a handle on the whole circuit.
Think of it like this. The passive components are basically the plumbing of the ECU. They're the pipes, the valves, the little tanks that just direct and control the flow of electricity. Active components, on the other hand, well, they're the brains of the operation. They're the ones actually making decisions, switching things on and off, and making the engine run.
Let's start with maybe the most common passive component of all, the resistor. Its only job is to resist, or limit the flow of electrical current. On the left, you've got the old school style, the color-coded through-hole ones. And on the right, you see these tiny little black rectangles. Those are the modern surface mount devices, or SMDs. You'll find them in pretty much every ECU today. Same job, just a much smaller package. Next up, we've got capacitors. Now, I want you to think of these guys as having two really important jobs. First, they're like tiny rechargeable batteries that can charge up and discharge instantly to smooth out any dips or spikes in voltage. And second, they're kind of like electrical shock absorbers, filtering out all that unwanted high-frequency noise that could mess with sensitive signals. They are absolutely critical for a stable and clean power supply.
All right, so let's get back to our car, the one with the no spark problem. We've got the basics down now, so we can start playing detective and hunt for the real root cause of the failure, right here on the board itself.
So, the command to make a spark, that starts in the microprocessor. But the actual heavy lifting, the part that switches the high current for the ignition coil, that happens over here, in what we call the output driver section. And this is the job for our key active components in this area, the transistors. They're basically high-power, super-fast electronic switches. Now listen, not all transistors are the same. In an ECU, you're mostly going to run into two types. You've got the MOSFET, which is a real workhorse. It's great for controlling things like fuel injectors. But for the incredibly fast switching you need to collapse the magnetic field in an ignition coil, you need something special. That's the IGBT. It's a special hybrid transistor, and for our no spark problem, it is suspect number one. When these things fail, they often short out internally, which you can easily test for with a multimeter.
So this all builds up into a really clear chain of command. The microprocessor, our CEO, sends out a little low-voltage command, usually a 5-volt square wave signal. That signal zips over to the output driver section, where it tells our IGBT to turn on and then, just as quickly, turn off. That sudden action grounds the ignition coil, and bam, it fires. If any link in that chain is broken, especially that IGBT, you get nothing, no spark. Okay, so that IGBT is definitely the star of the show for our ignition circuit, but it can't do its job all by itself. No way. It relies on a whole team of other critical components that provide the power, the timing, and the logic. Let's meet the rest of the team. Right at the very heart of the board, you'll find the microprocessor. This is the big boss, the CEO. It takes in all the data from the sensors, it runs millions of calculations every second based on the fuel maps and its memory, and it makes every single decision. When to fire an injector, when to make a spark, and it only speaks one language. Digital. Ones and zeros, which just means 5 volts and 0 volts. But how does our CEO keep time? Well, that's the job of this little metal can right here, the crystal oscillator. It's like a metronome, or maybe a heartbeat for the microprocessor. It provides an incredibly precise, super stable clock signal millions of times per second.
Without this steady pulse, the microprocessor has no idea what to do, and the whole ECU just stops working.
So the microprocessor and all those other sensitive chips, they need a perfectly stable power source. But a car's electrical system, it's messy. The voltage is jumping all over the place, maybe between 12 and 14 volts. That's where these guys come in, the voltage regulators. A super common one is the L7805. If you look at it from the front, the pins are input, ground, and output. It takes that messy voltage in, and on that third pin, it puts out a rock-solid, totally reliable 5 volts. If this component dies, the ECU is dead. No communication, no lights, nothing.
So here's a quick little cheat sheet to help remember our main passive players. A resistor is like a dam. A capacitor is a mini battery or a shock absorber. A diode is just a one-way valve, which is super important for protecting circuits. You can check them with the diode function on your meter. And a coil, or an inductor. It stores energy in a magnetic field, mostly for filtering signals. Simple ideas, but together they make the whole thing work.
Okay, theory is great, but let's get practical. How do we actually use this knowledge on the bench to test these little guys and find the fault? It's time to grab your multimeter. Reading these tiny little SMD resistors is actually pretty easy once you know the trick. For a 4-digit code, like this 3162 you see here, you just take the first 3 numbers, that's 316, and the very last number tells you how many zeros to add on the end. So a 2 means we add 2 zeros. That gives us 31,600 ohms, or what we'd call 31.6 kilo ohms. See? Simple.
Now what if you see an R somewhere in the middle of the number? Well, that's even easier. The R just stands for the decimal point. So a resistor that's marked 1R2 is just 1.2 ohms. One marked R33 is 0.33 ohms. It's just a simple shorthand, so they don't have to print a tiny little dot that you can't see.
Now, to do this kind of component-level work right, you need the right tools. A good multimeter is a must-have, obviously. You'll need a way to desolder things, some fine-point tweezers, and some kind of magnification. But listen, the most important tool on this list is that anti-static wrist trap. These components are extremely sensitive to static electricity. One little zap from your fingers can totally destroy a microprocessor, and you won't even feel it. Always, always be grounded.
And this is where it all comes together. We can now connect those real-world symptoms directly to specific components on the board. If the ECU is totally dead, the first place you go is the voltage regulator. Check for that 5-volt output. No spark on one cylinder? Go right to the IGBT for that cylinder. Look for physical signs of failure too. Little burn marks or a cracked casing can be a dead giveaway. An injector isn't firing? Find its MOSFET driver. This, right here, is how you go from being a parts changer to a real diagnostician.
So the next time you've got one of those mysterious electronic faults that's driving you crazy, don't be afraid to look inside that black box. With a little bit of knowledge and the right approach, you can actually read the story that the circuit is telling you. The clues are all there, just waiting for you to find them. So what story is your next diagnosis going to tell?